are three circuits. It's on autofocus. There we are. All right. And what those circuits are is series parallel number 1 is the first circuit that's on my breadboard on the far left-hand side. So series analysis number 1 is the circuit that's over here. And what it is that you can see, if I scoosh this up and scoosh this up this way, you can see better the relationship of the layout of the components. So I have an R1 that's designated as for analysis number 1. I've got R1 designated as a 2 kilo. I've got a 2 kilo ohm resistor here. And I tried to build them on the board very much the same way that these components are laid out in the schematic, meaning that my source will be coming in from this side, or in other words, from the top will be one end of the source coming into R1. R1 is positioned horizontally, and then it connects through a jumper to 2 and 3, which are parallel with each other, and 2 and 3 are parallel through this jumper, that green jumper at the top, and then they are parallel to the return rail to the source using the yellow jumpers down here. Now that same circuit pattern is demonstrated not only for analysis number 1, but also analysis number 2. So analysis number 2 will reflect the middle circuit, and the middle circuit has a 10K ohm resistor as an R1, has a 2K ohm resistor and a 5.1K ohm resistor in parallel with each other. And that's circuit analysis number 2, and you'll have that built because we will be measuring circuit analysis number 2 when we get back to lab on Monday. Then you have another analysis to work out. By then you'll become super experts in this. You get one more practice at this, and that's circuit analysis number 3. And here, same resistors, but all mixed up in different order. Now I have a 5.1K ohm resistor as my R1 series resistor, and my parallel resistors are 10K and 2K. Here's my 10K and my 2K. And somewhere on my table is a missing yellow jumper, but there's supposed to be one more yellow jumper that's on here. In any case, those are your circuits that you should pre-build on the board before getting to lab. I was a bit surprised that I didn't remind everybody to be sure to have these built before coming to class. And because I didn't remind everybody to build these before coming to class, or remind everybody to keep the circuits built on the board until they come to class, a number of students had not had these circuits built and therefore had to use class time, lab time, valuable lab time to build these circuits. Now some of these they're all meant to be very easy to build, but some of our circuit building skills were challenged, and some people took longer than others. And the unfortunate result of that is if we use class time, lab time, to build circuits that could easily have been built outside of class, we lose our lab time, precious lab time. So if you would all please be kind enough to build these circuits ahead of time, especially 2 and 3, because those are the 2 that you're going to be measuring. I'm going to do one with you together in this session. So let me pull out that document, and now we'll be looking at series parallel number 1. One of the very first things that you want to do is to make your predictions that you have an understanding of how to solve a simple series parallel circuit. And as I mentioned before, your solution will always be try to look at the point of the circuit farthest away from the source and look back in the circuit and see if you see any simple relationships that can be resolved. And a lot of our practice this past week with basic circuits analysis, the sim that you've had to do certificates uploaded for, and this week we'll be doing the DC circuits challenge, we'll be doing, and what's assigned is not all 12 in this case, but number 1 through number 10. So you should have had pretty good practice with this already, and let's go ahead and review your confidence in being able to solve a series parallel circuit of this sort. So what would be the first thing that you would like to do in this analysis? You have the upper, let me go ahead and bring this up. Okay, and focus. You have an upper VIR chart that is intended for you to record your peak voltages and peak currents. And then you have a lower VIR, and this is intended for your RMS voltages and RMS currents. And oops, this is an 8-volt peak. So the voltage source is an 8-volt peak. So what would be the first thing we would do to fill in the information in the upper table? Who would like to volunteer a solution? What would be the first thing that you would do?
Resistors.
Okay, let's go ahead and put in the resistors. So the resistors are given in this particular case, 2K, 5.1K, 10K. So 2 kilo ohms, 5.1 kilo ohms, and 10 kilo ohms. And these are the same here, 5.1 kilo ohms and 10 kilo ohms. What else would be something that we could fill in?
Total voltages.
Okay, well, let's go ahead and put in our voltages. So for our peak voltage, we're given that the source is an 8-volt peak. So if we're looking for peak voltage and you're given that this is peak, we could just simply write 8 volts peak right here. 8-volt source is the peak, but we want to write down what the total is for RMS. How do I determine my voltage here? Because that's not given. I'm only given an 8-volt peak waveform. How do I determine the RMS version of an 8-volt peak?
A times square 0.5.
Okay, so we would use our square root of 0.5 calculation. So turn the calculator on, square root 0.5 equals, and then we multiply this by 8. And when we go to do so, what is the value you calculate, Wei-Ji? Everybody?
5.66. 5.66 V RMS.
Okay, I would agree with you. If you look at the display of the calculator, it does show 5.6565. And so that third digit rounds off the 0.65 to become 0.66 in our calculations. So we will write down 5.66, and we have to write down VRMS. Okay, so far so good. So we have given resistances, we have a given voltage source, we filled in 8-volt peak here, converted the 8-volt peak into VRMS. This is a really good start. What would be the next thing that we should be doing? Yusuf, what do you think?
We want to calculate the voltage for the resistors in the parallel circuit.
You want to calculate the voltages for the parallel resistors. And how would you go about calculating the voltages in the parallel resistors? That would be R2 and R3. We don't have currents. And how would you find these voltages if you don't have these currents?
With a voltage division.
Mm-hmm. We could use that approach, but something's missing before you can use voltage divider.
Our currents.
And how would we find our currents? Because I don't have a voltage in order to calculate a current. I don't have a voltage to calculate this current. I don't have ohms to calculate this current.
So we should be able to find the voltage for the first resistor.
How would we find the voltage for the first resistor?
We just deduce that it's 8 volts peak because 8 volts is going out, so there must be 8 volts coming back in.
Well, okay, that's a really good hypothesis. We have 8-volt source, correct. 8 volts is being supplied to the entire circuit. So as 8 volts is being supplied to the entire circuit, not all 8 volts peak is going to be measured across R1. Part of it's across R1, part of it is across this parallel. So we've done this, a series parallel analysis, maybe a week and a half ago. What do you think we should do, Jackie?
You should find your total resistance.
We should find our total resistance. Okay, that would be good. And how would we go about finding our total resistance?
First, we would use reciprocal formula for R2 and R3, and then we would add whatever that turns out to be to R1.
Okay, that's a very logical approach. So here's here's the method by which we solve our series parallel circuit analyses. You have to do this. You have to simplify. And you simplify by what? By redrawing. And what are you redrawing? You're redrawing this circuit. So how do we redraw this circuit? We have 3 resistors, but we can see that 2 of these are in parallel. So if you recall, I'm going to move this over here so we can have a little more space on the side here. If you recall, I'm going to do this, yeah, we'll do it this way, and use this. All right. We can combine these 2 into a single equivalent resistance. So we should redraw our schematic so that we would have an R1, we would have an REQ1, if you recall. And REQ1 is equal to what? REQ1 is equal to R2 parallel with R3. So as they are parallel in this redraw, what it is that we need to do is to calculate what they resolve to be in parallel. And your classmate said, let's use reciprocal formula. So we're going to take the 5.1K ohm resistor, we're going to reciprocate that, then we're going to add it to the 10K ohm resistor, reciprocate that, and then equals and hit reciprocal. So let me write this out on the side here. Scoosh this over. And so our REQ1 is equal to 5.1K ohms in parallel with 10 kilo ohms. And the way we do a parallel calculation is going to be 5.1, and you do your exponent 3. So there's your 5.1 kilo, but we have to hit our what? Reciprocal key, yes? There's your reciprocal key. Then we hit plus. Then we're going to do 10 exponent 3, and we're going to reciprocate that, and then hit equals. Then we have to hit reciprocal one more time and hit equals one last time to complete our calculation for this parallel relationship. When you go to do so, Yusuf, do you have a calculation for us on this yet? Or would like everybody to try this?
5.38 kilo ohms.
Reciprocal plus 10 exponent 3 reciprocal. Oh, helps if I turn on the calculator code. 5.1 exponent 3 reciprocal plus 10 and 3 reciprocal equals. And what do you calculate there, my friend?
I had 5.38 kilo ohms.
Well, 5.38 kilo ohms. I'm looking for REQ1. I'm only looking for the ohms of these 2 guys in parallel.
I already jumped way ahead, huh? Hold on.
Yes, you did. So let's find REQ1. That's this value, okay? You had calculated it, you had added it to the 2K, you gave me the value of our total. So let's take this. This would be 3.38 kilo ohms, yes?
Yes.
So 3.38 kilo ohms is what these two guys work out to be, 3.38 kilo ohms. And so when you go to look at this, schematic, you now have reduced 3 resistors down to 2 resistors that are in series, because here is your AC source, like so, right there, and you have 2 guys here, and this one's 2K. So now that we have resolved these 2 in parallel, giving us 3.38K, we realize that that is in series with the 2K, therefore your R total is in fact 5. Our worksheet again. And we have 5.38 kilo ohms. Everybody okay with that? Okay, that was the value you had shouted out earlier, which is absolutely correct. And you should double check this calculation. So I leave it to you to double check the parallel. I'll leave it to you to make sure that you are confident with the reciprocal calculations that we have done over here, that you are confident with reducing 3 resistors down to now 2 resistors that are in series, and in series that our total is 5.38 K ohms. And I'm going to write that down here, 5.38 K ohms. All right, so now we have an R total, and we double checked it, triple checked it, we're happy. What do we do with this information now? Question goes to Wei-Ji. What do we do now?
Calculate the I peak for total I
Calculate
peak.
I peak. Okay, we can calculate I peak. I have an 8-volt peak. I have these ohms over here. So let's go ahead and do that. Let's take 8 and divide by 5.38 kilo, exponent 3. And what is your calculated current, sir?
1.49 milliamp peak.
1.49 milliamp. Okay, that we calculate to be 1.49 milliamps. Yes?
Yes.
Okay, everybody happy with that? All right, so this would be 1.49 milliamps peak. Okay, while we have that peak value on the display of the calculator, could we immediately convert that into RMS? Yes. By doing what, Wei-Ji? How do I immediately convert this into the RMS equivalent down here?
Use the times the square root 0.5.
Okay, so times my square root 0.5, and now equals, and does your RMS value calculate to be, everybody, 1.05 the RMS, milliamps RMS, 1.05 milliamps RMS, 1.05 milliamps RMS. And you should be double checking that peak current. You should be double checking that RMS current, okay? Easy enough to do. If you're confident with these values, then Jackie, what would you do next?
So we know that current in a series circuit is the same, so we can write in for IR1 peak and IR1 RMS.
Ah, okay. Did everybody hear that? That in this series circuit, because this thing that I've drawn in blue is the only series circuit we have. This is series parallel. But in this simple series circuit, where I happen to have a current flowing through these 2 components, we know the peak current as an I total. We also know the RMS as an I total. Doesn't the total current flow through an original circuit resistor R1? Doesn't that tell you that the 1.49 milliamp peak, which is total current, is also the current flowing through this first resistor? And we can go ahead and fill that in. 1.49 milliamp peak, and then the RMS 1.05 milliamps RMS. Okay, so far so good. Excellent. Now, the next question, Yusuf, what will we do next?
Or you could easily use Ohm's law to do R1 voltage peak.
Okay, let's go ahead and use Ohm's law and calculate this voltage, because all we need to do in order to calculate that voltage is simply going to be my current times resistance in order to give us our voltage, yes? So I have a current, I have a resistance, and if I multiply these two guys together, won't I get that peak voltage? And by the same token, if I multiply the RMS current times this ohms, won't I also have the RMS voltage over here? So let's go ahead and do that. Yusuf, can you go ahead and take 1.49 milliamp peak and multiply that by 2K? And Wei Ji, can you go ahead and take the RMS current, 1.05 milliamp RMS, multiply by 2K, and give us the RMS voltage?
So we got 2.1 RMS, 2.1 volts RMS.
Okay, so Wei Ji says for RMS, we will have 2.10 VRMS. And Yusuf, what do you calculate for the peak voltage, please?
2.98 peak voltage peak.
So 2.98 V peak. Excellent. Great. Now, if we had this 2.98 V peak, could we double check this RMS by multiplying this value by the square root of 0.5? Could we do that? Let's go ahead and double check that. Our 2.98, multiply this by square root 0.5. Let's see how close we come to 2.1. How about that? 2.107, and the reason why it's not exactly the same, because we're using rounded values, yes? So are we happy with both of these values for voltage for R1, 2.98 volt peak and 2.10 VRMS? So far, so good? All right, next quantity. Jacqueline, what would be the next step? We have two currents and two voltages left to do. What approach would you use at this point?
I would use our current divider formula to find I peak and IRMS.
Okay. We could use our current divider formula, and the way current divider formula works, if you recall, we have a certain amount of current that's flowing through R1. We said that that current was 1.49 milliamps peak, and it does flow into this node where it splits. Part of it will split there, and then the other part of it will split to come down here. So how much splits into each of these branches can be determined by current divider, and so we can use current divider as one method of finding these currents. There's another approach that I don't want to discount. We can also do this. Could we start with our 8-volt peak? And since we're happy with the 2.98 volt peak across R1, look at this 8-volt peak, and you have 2.98 volts peak across R1. Watch this. 2.98 volt peak across my R1. And I have an 8-volt peak source. Could I take the 8-volt peak, subtract the 2.98, to find how much volts peak is going to be dropped across the REQ pair? Is that another way to find a voltage which would then allow us to find currents? That is an alternative method. So I don't want to discount that that is a method, okay? But let's go ahead and review current divider, and then we'll go ahead and use the other method for the RMS values. So current divider, let's go ahead and flip the page and do this and look at our schematic. And hopefully everything appears. Good. So we will do current divider. And current divider works only for parallel relationships. So what do we have? We happen to have two resistors. We happen to have an R2, we happen to have an R3. This is 5.1 kilo ohms. This guy is 10 kilo ohms. And together they formed a singular REQ1 that was 3.38 kilo ohms. So our current divider was written this way: IRX, meaning current through a particular resistor, was equal to R total over RX times I total. Now that's the general form of the formula. If, however, I was looking for IR2, how would I fill in the quantities of the numerator and the denominator specifically for IR2, specifically for this particular circuit here, G? What would I do here?
We use 3.38 kilo ohms divided by 5.1 kilo ohms.
Mathematically, you are correct. I was looking for you to say REQ1 over R2. Always start with writing out the formula we're going to use, and then we'll fill in the numbers. But you're absolutely correct. So it says RT for our general formula, but RT is not going to be the R total for the entire circuit. RT can only apply to that combination that is in parallel. That combination that was in parallel is REQ1. And that's why that goes in the numerator. So let's go ahead and now fill in these values. I'll scoosh this guy up and fill in these values. This will be IR2 is equal to 3.38 kilo over 5.1 kilo and multiply by 1.49 milliamps peak. Could everybody do that? Do we have to key in kilos, or do the kilos cancel each other out?
Nope.
They'll cancel each other out, so they will disappear. So there's no kilos as part of this calculation, but there is a milli, so don't forget to key milli into your calculators. So let's go ahead and do that together. Turn it on, 3.38, and divide by 5.1, and multiply by 1.49. Oops, 49, exponent change sign 3, and your calculated result, sir? G?
987.49 microamp peak.
987.49, and it does show 10 negative 6 here, yes? So that's what we're going to write down, 987.49 microamps peak, okay? And so by the same token, we're going to calculate the other current, and the other current will be IR3. And so IR3, let me just keep moving this up. Here we go. Okay, so IR3 is going to be equal to REQ1 over R3 times I total. And when we go to fill in the numbers, this will look like IR3 is equal to 3.38 over 10 times 1.49 milliamp peak. And notice I didn't write down kilo or kilo because they cancel each other out anyway. No need to write that out. So let's go ahead and do the math. And Yusuf, can you double check our values here while I'm doing this? So 3.38 and divide by 10 and multiply this by 1.49, exponent change sign 3. So what do you calculate for your peak current going through R3?
503.62 microamps peak.
Okay, and we concur, 503.62 microamps. So we'll fill that in, 503.62 microamps peak. And notice that we do write down everything in peak. So once we have these peak currents, can we now go ahead and finish up the upper chart with our peak voltages, yeah? Let's go ahead and do that. So, Jackie, if you could calculate the peak voltage for R2, and Weiji, if you could calculate the peak voltage for R3, let's go ahead and see if we have concurring results. We're going to multiply this current times these ohms to give us a voltage here, and this current times these ohms to give us a voltage here. Let's see what happens as a result. I'm going to do the lower one first since it's on my calculator, and multiply by 10. And it looks like, from my calculator, I'm going to get 5.04 volts peak. And Jacqueline, what do you calculate?
I also calculate 5.04 volts peak.
And yes, we concur. 5.04 volts peak. Excellent. And Weiji, you did get that calculation, 5.04 volts peak, yes?
Yes.
Okay. So we're done filling in the upper table. How did we fill in the upper table? We used current divider formula. Current divider formula was a good reminder for us of how to find branch currents of a parallel relationship. The RT in this formula, as a reminder, is not RT for the circuit, but it is RT only for the bank of resistors, which was REQ1 of 3.38 kilo. So we calculated the branch currents in peak, multiplied by ohms, got peak voltages, and it's interesting how this current, so different from this current, and these ohms so different from these ohms, when we multiply them by each other, how could we coincidentally get the same voltage? How is that possible? Is that coincidence or was that intended?
Because they're parallel.
They are in parallel. 2 and 3 are in parallel. They better have the same voltage, okay? All right, let's use a slightly different approach for the currents and voltages for RMS. So what I said that you could do is, if we review this circuit here, we had an 8-volt peak, yeah? We had a 2.98 volts peak across this resistor. What's left over must be the difference between these two, yes? Well, by the same token, if this is your total voltage in RMS, and that was the voltage across R1, then the voltages across 2 and 3, shouldn't that be the difference of this subtract this? Let's go ahead and try that out. Let's go ahead and do this. Let's take the clear 5.66 and let's go ahead and subtract 2.10, and we have a RMS voltage that looks like 3.56 VRMS. And the way that that looks is right here. This might help you out. We have, move all this over. We have a source. We have these two elements, REQ1. We have R1, and we have a VS, and the VS was 5.66 VRMS. We calculated a 2.10 VRMS across this guy. There. This is between here and here. So would it make sense that if I wanted VREQ1 would be this value, subtract this, will give us what's left over. And when we go to do so, what value do we get? I get 3.56 VRMS. So from here to here, we have 3.56 VRMS. And because this was a parallel relationship between these two original resistors, don't I have over here 3.56 VRMS And don't I have over here also 3.56 VRMS? Isn't that true? Huh.
Yes.
Let's go ahead and see if you feel confident about this value. So this value was found how? This was found by using subtraction of this 2.1 volts RMS subtract from the source of 5.66. Could we, if I go to take a chance, I'm going to fill this in, 3.56 VRMS, 3.56 VRMS. Could we convert the 5.4 volt peak into RMS and see what happens? Given 5.04 volts peak, and you now want to convert to VRMS. What do? Don't we multiply this by square root of 0.5? So VRMS equals square root 0.5, and we're going to multiply this by V peak. So here's your calculator. Square root 0.5. We're going to multiply this by 5.04. 5.04. When we go to do so, hopefully we'll have something pretty close to 3.56. And the calculator shows us what? 3.56. So in this particular case, can the subtraction method give us a voltage across REQ1, which is the pair of parallel resistances? And didn't we double check this by converting the volts peak into RMS? So we're feeling pretty good about these voltages being across R2 and R3 as being our RMS values. If you're happy with that, now do I have enough information to use Ohm's law to calculate the two remaining currents? Let's go ahead and do that. Yusuf, could you calculate IR2 in RMS using Ohm's law? And Jackie, could you calculate IR3 using Ohm's law? So Yusuf, we're going to take 3.56 and divide by 5.1K. What do you calculate, my friend?
698.04 microamps RMS.
698.04 microamps RMS. You notice I made these columns nice and wide so you can fill in all the values. Isn't that nice? Okay. And then the other value, Jackie?
356 microamps RMS.
Okay, so you calculate 356 microamps RMS. Let's do a spot check. Let's go ahead and check if this 987.49 microamp peak does convert to something close to this RMS current. Let's double check that. Let's go ahead, take 987.49 exponent, change sign 6. So what I have in here is that microamps. And how do I convert that into RMS? I multiply by what? Square root of 0.5, yes? And hopefully my calculator will show me something that's pretty close to this value. Engineering, 698.26, 698.04. Again, close enough because, again, we're using very rounded values, okay? And then by the same token, if we converted this peak value of current, 503.62, exponent change sign 6. Now I have the 503.62 microamp peak. Multiply this by square root 0.5. Hopefully I'll get something close to the 356 microamps RMS. Boom. Engineering. How about that? 356.11 microamps RMS. Close enough considering this is the last of a sequence of rounded off values. Are we standing pretty good on these two tables? Because we're going to be confirming our measurements in peak. We're going to be confirming the following measurements. Following measurements will be confirming will be our peak values using the oscope, RMS values using digital multimeter, RMS current using digital multimeter. And then how about voltages at these points, point A, point B, and point C? Point A is here, point B is here, point C is here. B and C are the same point measured to ground, yes?
We can't see where you're pointing.
I'm sorry, you're right. We'll scoosh this down. Thank you. So we're looking for, and let me go even further. You can see all of it. Camera. There we go. Focus. Yay. All right. So now we're looking for voltages point A, point B, point C. Point A is here, and isn't that across the source? So if that's across the source, don't I expect my full 8 volts peak here? Point B and C are electrically the same. This is B, hidden behind the little V block. Point C is there. And aren't they electrically the same point? And they are measuring across R2 and R3. We already determined that the peak voltage from across both of these should be about 5.04. So point B should be 5.04 volt peak. And same here, 5.04 volt peak. Now, how do I calculate period? Question goes to Wei Ji. How do I calculate period?
We just reciprocate the frequency.
Reciprocate the frequency, yes, and the frequency is given as 3.5 kilohertz. So I will take 3.5 kilo right there and hit my reciprocal key. And when I go to do so, what do you calculate there, Wei Ji?
285.71 microsecond.
Okay, 3.9, okay, and then I'm going to reciprocate this, and you have 285 point what?
71
and it's microseconds.
microsecond.
Excellent. So 285.71 microseconds. Keep an eye out for that because we will confirm this on the oscope and we will also confirm this in multisim. So at this point, we're done with all of our calculations. Now it's time to hook things up to this circuit. And this circuit, as I've said, is already built for us right here. This part of the circuit's already built along with your analysis number 2 circuit, analysis number 3 circuit. So if we look at the page, the second page to fill in, the second page to fill in asks us for these measurements. So we should measure the R values first. Now, when I have all of these built, this is nice and pretty, but if I keep these other components on the circuit, it will seriously and adversely affect my measurements of the resistors that are here. So what I want to do is this. I want to, just for this segment, pull this jumper, set it aside, take this, pull this jumper and set it aside. So now circuit number 2 and circuit number 3 are no longer part of the board, okay? I only have circuit number 1 being on the board. And if I want to measure the resistance of resistor number 1, I simply get my ohm meter and my ohm meter, turn it on, go to omegas. So you can see the display of the multimeter. You can see the circuit. So, okay, let's go do this. First thing you want to do, turn on the multimeter, make it go to a continuity test. You'll always want to make sure your banana connectors are in the appropriate position. So black goes to COM, red goes to the V omega hertz. And then you want to do the continuity test. Okay. It does beep. We have continuity. We're ready to go. So we're going to go ahead and connect across R1, which is supposed to be our 2 kilo ohm resistor. And the measurement in this particular case, auto kilo, and I happen to have 1.988 kilo, which I need to write down on my sheet here as 1.988 kilo omegas, okay? Now, in order to measure R2 and R3, they're presently hooked up in parallel with each other, so if I go to hook up across either one, I'm going to get the combined equivalent resistance. Let's go ahead and double check that because we calculated the equivalent resistance of these guys together as a pair to be, what, 3.38 kilo? Let's see if they actually work out that way as a pair in parallel. So all I have to do is leave the jumper wire in place, leave them connected to the bottom rail, hook up that hook there, and hook up this guy here, and lo and behold, I get my 3.369, which is pretty close to our 3.38. 3.37 now, even better. There, 3.37. Okay, well, we're really interested in the individual resistances, so I'm going to yank this jumper. No. Okay, so that jumper is now removed, and now I'm measuring across a singular resistor, which is my 10K ohm, and what do I measure? I measure 9.98 kilo. So I'm going to write that down on my sheet for R3 as 9.98 kilo ohms. There we go. And we have one more resistor to measure to verify that it is in the right place. So you can do all these resistance measurements at home. Don't wait to come to class to do these resistance measurements for circuit number 2 and circuit number 3. Circuit number 2 and 3.
We're not supposed to be copying off of you right now.
You can copy, yeah, for this particular exercise, that's fine.
Okay.
But when you go to do this on Monday, you can pre-measure the resistances at home. Okay, don't wait to come to class to do the resistance measurements since you have a very nice digital multimeter. Again, we want to work smarter, not harder. We want to do whatever we can at home, whatever we can do here. So now I'm measuring the ohms of R2, and that's supposed to be something close to 5.1, and I happen to have, what, 5.09 K ohms, yay? Pretty good. So it is the right resistor in the right position according to my schematic. That's very important. You have to verify while you're doing your circuit builds, the correct resistor is in the correct position on the board. That's your job. Okay, so we're happy with that. And I'm going to write down 5.09K. 5.09 kilo ohms. Very good. Now, what we're going to do is measure our total resistance. So our total resistance, hold on just one sec. Somebody's knocking at the door. It's, our team of techs, and they needed to confer with each other. All right, circuits rebuilt, and as the circuit's rebuilt, we need to measure total resistance. Now keep in mind, circuit number 2 and 3 are still disconnected. So if I want to measure the total resistance of this one particular circuit, all I have to do is go ahead and connect to my rails. Yes, if I connect here to the positive rail, if I connect here to the negative rail, I will be measuring the total ohms of this circuit only. And we expect something close to 5.38. So I'm going to go ahead and connect that guy there, connect this guy here, and my total ohms, my friends, works out to be pretty close to 5.38. Oops, I'll take the 5.37K and I'll go ahead and write that down. 5.37 kilo ohms, which is right there. Okay, so are we done making the measurements of our resistances? Yes. Now we have other things to do. So when you go to do your measurements of resistances, what do you need to verify at home? You need to confirm that the correct resistors are in the correct positions. What does that mean? So for circuit number 2, here's circuit number 2. So for circuit number 2, you're supposed to have the 10K ohm resistor here. Measure it and confirm it is 10K. You're supposed to have the 2K here. You're supposed to have the 5.1K here. That's for circuit number 2. You measure these, and if they're in the wrong places, you got to fix it. It's got to be fixed before you come to class. Then for circuit analysis number 3, here's circuit analysis number 3. You have to confirm for the third circuit that your series resistor is a 5.1 kilo, R2 is a 10 kilo, R3 is a 2 kilo. The circuit build has to have the correct resistors in these positions. Otherwise, when we're going to go to measure currents, something undesired results will occur, and we don't want that to happen. All right, now we're ready to go to the next step. And what we did on Monday was something pretty exciting. We introduced all of us hands-on to our signal generator and our oscilloscope. And there you are. There's our signal generator and our oscilloscope. So signal generator here, oscilloscope over here. We need to set this to, we turn it off and then turn it back on. We need to set this fellow properly for the parameters that are desired for the first circuit. And then we're going to measure the AC waveform over here. So let's go ahead and do that. The parameters that you're given on your paper were 3.5 kilohertz at an 8 volt peak. So if we go to bring this fellow really close, and we'll bring this up really close, something like this. Okay, is that pretty clear for everybody? Give me a thumbs up if it is. Good. All right, so we basically have our face right up in front of this machine. On-off switch is here. Your BNC connector is this guy here. So we're going to connect to what's called the main output. And we're going to spin this guy on. This is a bayonet connector, has pin at 6 o'clock and 12 o'clock, and it has to line up on our connector this way. Push in, give it a twist, and when it twists, it will come to a lock, and when we pull on this, it will not come loose, okay? Now, hold on just a moment. I'm doing a lecture, I'm sorry. Goodbye. All right, so now we want to change, when we first turn it on, the flashing cursor is on frequency, and we need to move the cursor from here to a different field where all the numbers are. Here's your field button, move left, move right. So I'm going to press the move right. And now notice the flashing cursor is on the 1 digit. I don't want it there. I do want it on this side of the equal sign. I have a digit control, digit left, digit right. So I'm going to move the digit to here. It is now flashing on 0 right next to the decimal point. I can put my finger into the dimple of my nub and rotate this in a counterclockwise fashion. Do you see the value going from 10K to 9K, 8, 7, 6? Where do we want this, everybody? 3.5, right? So here's 3. The way I get to the 0.5 is I'll move the digit one more space. So here's my digit right. Now is the cursor flashing behind the decimal point. So now I'll raise this up to 5. So now do I have 3.5 kilohertz? Everybody good with that process so far? Next, we want to make sure that our volts peak is going to be 8 volts peak. This guy says 20 volts peak to peak. Well, I have to change from frequency to amplitude. So amplitude now moves the cursor down to the second row for V high Z for volts. And presently the field on this side of the equal sign says I've got 20 volts peak to peak, which is 10 volt peak, right? 20 volts peak to peak is 10 volt peak. I need to get this to 8 volts peak, which would be what? How many peak to peak? 8 volts peak is how many volts peak to peak? You're right, 16. So I need to move the field first from here to here. So here's my field button, field. Now this is flashing. And I want to move to the next digit over, digit. So now I have the digit in front of the decimal point. And now I'm going to rotate the knob until I get to 16, 19, 18, 17, 16. Everybody okay with 16 volt peak right there? Peak to peak. So 16 volt peak to peak should give me an 8 volt peak waveform. One last thing that you need to do, you want to make sure, make sure we're on sine wave. Make sure we're not on square wave. Make sure we're not on triangular wave. So make sure it's on sine wave. And then also, nothing will happen unless you press the output button. Right now, there's no LED lit. So I have to press the output button. Now we have an LED lit. With the LED lit, now I'm actually getting signal out of my cable onto the board. This guy is now set. Any questions on how to set our function generator for frequency and how to set our function generator for amplitude? So far, so good? It's a review of what we did Monday, and you'll be reviewing these procedures again when you come back next week, Monday. All right, now let's go ahead and connect this to our board. So our board, again, right here, circuit 2 and circuit 3 are still disconnected because I left the jumpers here, but I do have a connection point for my signal source to come into the top red rail, and I do have a connection point down here with this jumper to go to my ground side. So on the other side of my Oscilloscope, on the other side of my signal generator leads are a pair of hooks. So I'm going to go ahead and hook the red hook here, like so, and I'm going to hook the black hook here, like so. And they are now hooked up and on the board and not bothering anybody. Try to get them out of the way as much as possible. Okay, so now I have applied signal onto this entire red rail. I have applied the ground side of the signal to the entire blue rail. Can I make a measurement of these? Yeah, because on the other side of the board, I have another jumper for me to hook up my oscilloscope probe for positive and negative. And yes, I am supplying my circuit from the red rail to the blue rail. Now, on the oscilloscope, this is what you have. There's our friend the oscilloscope. And the oscilloscope, I have an oscilloscope probe. This is quite different. This one in appearance, it still has a BNC connector on one end, and it fastens onto channel 1. So we're going to use channel 1. Here's channel 1, 2, 3, 4 inputs. So we're going to use channel 1. So take this guy and fasten it on to here. Give it a twist. Lock it in place. Gentle tug. Now, if you look at this cable, it's quite a bit different from the little mini hooks you've seen before. It has a alligator jaws. This is what we're going to use for ground. And then this has a hook that comes out of this. When you go to depress this collar, it will reveal a little hook right there. See that little hook up here when I'm pushing? Yeah. So that little hook is what we're going to be using, and it only works when we push. Now, on the oscilloscope probe also happens to be a little slider switch, and the slider switch will go between 10x over here to 1x. 10x is a magnification. opportunity. We don't want 10x, we want to leave it on 1x. So slide it back, slide it forward, make sure it is on 1x. The ground, the alligator ground wire is fastened securely onto a shaft, but it can be spun around, okay? So for convenience purposes, after you hook to your component, if this is coming at your circuit the wrong angle for ground, you can just spin this around and hook it up a little differently. So that's what's nice about this, is it does give you some flexibility here. Let me show you how we're going to hook this guy up. So on the board, it will look like this. Here's your board. We already have on one side our function generator coming in. On the other side, we're going to have our oscilloscope probe. I'm going to push this out and clip on there. And we said that the black alligator, I'm going to clip onto ground right. Come on, fasten. There we are. So now I have my oscilloscope connected on this side. I have my signal generator connected on this side. So the very first thing we want to do in our work is to verify that I think that gives you a pretty good view of our oscilloscope focus. All right, so after we turn this on, I won't turn it on now because it takes almost 3 minutes for it to go through its diagnostics before we even get a waveform. But after we turn it on and after the Tektronix screen comes on and saying, hi, we're Tektronix, we're wonderful, and it goes through a diagnostic procedure, after 2-3 minutes, then you're able to possibly see a waveform. There's a button over here, black on the right-hand side, called Auto Set. When I press this, the waveform is being analyzed, and boom, you will have the oscilloscope automatically set a waveform display for you. Now, what we need to do is to confirm the information on the waveform is in fact what we want. We had 16 volt peak to peak from our function generator, which is an 8 volt peak. We need to confirm this is 8 volt peak. So we look at this, you say, well, that waveform's a little small. We could start counting the squares like you did in your written exercises. But right now the waveform's a little small and there's too many cycles on the display. So let me show you a couple things we can do to not change the value of the waveform, but magnify it so we can see what we call with better resolution. Right now, our vertical scale is giving us 5 volts per division. Our time per division is 200 microseconds. So there's your vertical scale. Here's your horizontal scale. In order for me to make this waveform appear larger, and this is one of the homework questions we had talked about on Monday, when you're given an oscilloscope display and you have a display like this, what control do we use to make the waveform appear larger on the display? Do we play with the voltage control or do we play with the time control? So vertical has to do with voltage controls. These are all voltage control knobs. And horizontal has to do with the time. So in order to make the waveform appear larger, we want to play with vertical, which is our voltage controls. And since we're hooked up to channel 1, we have a couple of knobs and controls we can use. This is vertical positioning. And by virtue of looking at the yellow flag over here, that yellow flag automatically centers on the 0 line of your scope. If I go to move this vertical position knob, I can move the flag upwards and have it align with, say, this particular graduation line. There. I can have it, and if I have multiple traces, it would be advantageous to move one waveform up and another waveform down so you can compare them. But for the purposes of this discussion, I'm going to move this back to our 0 reference line. Right there. We are happy campers. But I do want to increase the display so it appears a little larger. So I'm going to play with my vertical scale knob. These are your scale knobs, scale. So these are your position knobs, position, 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 position. So I'm going to play with the vertical scale knob, and you are going to rotate 1 click to the right to magnify. In a moment. There we go. Right, one click to magnify. Did it magnify? Yep, sure did. And if I do a second click, what happened? The waveform is so big it went off the display of the scope. Useless to us. So which position do I want? One click back to the left or two clicks back to the left? No, one click to the right. That seems good. I have most of the waveform that's on the display. Recenter this guy and it looks centered, but I still have too many cycles. So here's another homework question. The other homework question asks, if you have many cycles on the display, what control would you adjust and how would you adjust it to reduce the number of waveforms on the display? Would you play with vertical voltage or would you play with horizontal time? You would play with horizontal time, and the horizontal scale is here. If we go one click to the right, I magnify. Give it a moment. There we go. And if I go one more click to the right, ooh, this is pretty good. I've got a whole cycle and just a little piece left over of other stuff. I can play with my horizontal position. And there, that's pretty good waveform. So in order for us to check the amplitude, I have something known as cursors. And if I press the cursor button one time, I can get one set of cursors, vertical cursors. If I press it, I get horizontal cursors. Press it and it goes away. So I want these horizontal cursors. Let's go ahead and adjust this guy so that it is up to the peak, and then adjust this guy so that it is here and at 2 let's see, here and here. So we happen to be counting, let's count the number of divisions. 1, 2, 3, 3 point, doesn't quite go up to 4. Looks like it's about 3.8 divisions, 3.8 times 2. Let's see what that works out to be. It's almost where we want it to be. So 3.8 times 2, 7.6 volts peak. Yeah, we're almost at a full 8 volt peak. Let's take a look. What else? Volt peak. Okay. Okay. And then we have, if we go to cursors this way, we can check the beginning of our cycle. Let's go here. You look for that little hash mark. There's a little hash mark right there, and then move the second cursor here until we are lined up with this little hash mark at the 0 line, as close as you can get it. And when you go to do so, it'll read a delta time. What is my delta time? Delta time is given as 286 microseconds. What did we calculate earlier is we calculated 285.71 microseconds. So the O-scope showing us 286. That's pretty good. So measured 286 microseconds. So are we okay with 286 microseconds here? So far, so good? All right. Now, let's go ahead and check our RMS voltages using our digital multimeter. And that will work out this way. Over here like so. Here's your circuit board. Here's your, take off the O-scope leads. Here's your multimeter. Set this up so that this is on AC volts. This up a little higher so you can see more of what we're doing. This. All right. And the probes will be red into volts, black into common, and then the knob will be to this V with the sine wave. And so now it's ready to measure AC. And let's go ahead and confirm our RMS voltage for the source. Connect there and connect here. So here's your source leads. We said that we expect to have something close to 5.66 VRMS, and we will have 5.56 VRMS. Very good. So 5.56 VRMS. You needed to make a voltage measurement across R1. The voltage measurement across R1 was estimated at 2.1 volts RMS. So all you have to do is take this and measure across R1. So this goes to this side of R1, and this goes to this side of R1. And we expected something close to 2.10, and we're getting right here at 2.817. So that's what we're going to write down. 1.817, sorry. 1.817 VRMS. We're still getting a little bit of that loading effect that we encountered before. We have much less a loading effect because our R total is many ohms compared to Monday. Monday, our R total was at 50 ohms. Here, our R total is in kilo. So why don't we go ahead and do this? Our waveform was a little low. It was 7.6 volts peak, and our VRMS is a little low. We still have some loading effect based on the signal generator. What I'm going to do is go to my signal generator, and on amplitude, come over to this side on amplitude, and I'm going to...
You can't see the screen. Are you supposed to?
Okay. All right. Let me get right up to the screen for you. That a little better for you, my friends? Focus. Okay. So what we're going to do is we're going to fine tune this to be a little higher. So my digital multimeter measures something closer to 5.66 VRMS. I'm going to rotate. 5.66. Won't take much of a nudge. But let me get my VRMS. 5. Oh, doesn't need much, but needs just a little bit. That's as close as I'm going to be able to get. So we're going to need 16.3 volt peak to peak, or 8.15 volt peak out of here in order to compensate for an internal resistance of 50 ohms that's inside this machine. And by cranking this up just a touch, bring this back to our circuit board. These measurements. Do I now have a voltage that's closer to our calculated 5.66? I'll go ahead and take that voltage, 5.66 VRMS, and so 5.66 VRMS. And now I'm going to measure across R1, right there, and right there. We had anticipated something close to 2.1. We're getting a little closer. This comes out to be 1.851. 0.851 VRMS. And if I go to measure our voltages across the bank here to here. So I said that for parallel, we can measure across either resistor or both resistors, and I'm measuring across both resistors. We expect something close to 3.5 VRMS. We get 3.158, so 3.158 VRMS. And they are same voltage if I move over here. 3.158 VRMS. Okay. How about currents? We calculated currents that would be something like 1.05 milliamps RMS. Now, currents are a little special because you have to do several things for currents. If you recall, and I'm going to bring this back up a little higher so you can see more of everything. What you needed to recall for currents was you had to set the multimeter properly, so the probe banana connector has to move from this side to go to millimicroamps. Then you position your knob over to milliamps. So it is measuring AC, milliamps. Probes are now set properly. In order for us to measure total current, we need to decide where to measure total current. And if you recall, total current went through the first resistor. So if I lift this jumper wire, if I lift this yellow jumper wire, I will create an open between the rail and the first resistor, and that's where I can measure my total current. Pull this guy out, bring my probes in, hook up my red probe here, hook in my other probe here, and I have to go from DC to AC. And for AC, this is showing me as 1.02 milliamps. So I will write down for the total 1.02 milliamps RMS. And what did we calculate? We calculated something that was 1.05 milliamps RMS, yes? So I'm going to write down on my measurement paper, because these are our measurements, and write down 1.05 milliamps RMS. We have two more currents to measure. The remaining currents are IR2 and IR3. So in order for me to do that, I need to very carefully rebuild this part of the circuit. So this has got to go rebuilt. And my current for IR2 is off of this jumper wire. And I can measure, using my hookup here, an open between here and here. So this black probe will go here, and the red probe will go here. And we hope to see something 600 and change microamps. I should go to the microamp scale. So there's the microamp scale. Let it stabilize. Everything stabilize. I have this in the right place, of course. Oop, there we go. Now let it stabilize. And what is not built? Oh, back to AC, of course. On, and then back to AC, of course, in microamps. And now let it stabilize. It comes into 698 microamps. We had predicted 698.04 microamps. Pretty darn good. So we will go ahead and write that value down in our measurements. So in our measurements, we will write down our 697 microamps. And we're good with that. Now the final measurement, in order for us to do this, we need to rebuild the rebuild the second branch. Now open between here for the third and hook up to the resistor and hook up to my ground, and voila, come on, hook, there we go. Let this stabilize. We had predicted what? 356 microamps, and guess what we measure? 358.1 microamps RMS. Fantastic. Those are the currents that you're going to need to verify for your calculations for circuit build number 2 and for circuit build number 3. All right. So this concludes, my friends, the discussion I wanted to have with you this afternoon for series parallel. These are your 2 builds. Your worksheets are presented to you. Series parallel analysis number 2, series parallel analysis number 3. Finish the calculations for peak and RMS. You also have a multi-sim exercise, and the multi-sim exercise is to do this in multi-sim so that it will appear, you'll do the paste in here, and you'll do the paste in here, and on your answer sheet. And if you do this properly, it'll look a lot like my sample here. This is my multi-sim for the series parallel for number 1. You'll do yours for number 2, and you'll also do yours for number 2 for measuring period, because you need to demonstrate measuring period on multi-sim. Any questions? Because our time is up. Any questions?
Are we doing the measurements on our home built circuits with the DMM?
You cannot, the only measurements you can do on your home build circuits is resistance. That's all you can do, is to verify the resistors, because you don't have the rest of this at home. You don't have the function generator or the oscilloscope. So these you have to wait till Monday, but you will be able to do this in multi-sim. In multi-sim, you can see the waveform analysis and measure period the same way I've done on this piece of paper, okay? So in multi-sim, you're going to do 2 snips. One snip will be to show your cursors measuring voltage, and the other snip will be your cursors measuring period. And with that, any other remaining questions?
Will we be measuring V peak on Monday?
On the oscilloscope, you will, yes. Yes, you'll be measuring oscilloscope V peak on Monday, and then with your digital multimeters, VRMS and IRMS on Monday for circuit number 2 and circuit number 3. Good questions. Any other questions, my friends? If there are other questions, and I've seen some good ones come up through Discord, shoot them into Discord, and I'm usually pretty good, unless I'm driving or something, to answer Discord questions pretty quickly. And Jacqueline, you got your solution for this afternoon's question. You figured it out, actually, so good job on that. With a little reminder from our friends, there must be a current parameter there somewhere that helps you out. So yes, I'm glad you figured that out. All right, my friends, then with that, I will go ahead and put us back into our friendly face view, gallery view, and I will wave at you all and put this into my camera front and take out my camera and take our happy, wonderful picture for the dean. The dean asks for these once in a while. All right, I'm in here somewhere, yes? Okay, Yusuf, get yourself in the picture here.
Damn it, I'm here.
You can do it. You can do it.
The camera is just weird.
The camera around a couple of times. Okay, 1, 2, and smile. Yay. All right, I got you guys. Good job, everybody. And we'll see you on Monday. Take care. Bye-bye now.